as additional practice, let's now do an example of an ODE with shifts. And in particular, let's try to solve y double prime plus 4y prime plus 5y equals f of t with 0 initial conditions, where here f starts at 0. So let me draw a picture here. This is t. So your function starts at 0 until we reach the value 5, at which point it just jumps up to have value 5 until 20. Maybe here at 20, where it goes down back to value 0. So this is your function f of t. And again, the way to interpret this is, well, first of all, f is literally an off switch. And here we have the mass spring equation with damping, where the force is off, on, and off. And as usual, what we have to do, we have to write f in terms of the jumps, because we want to take Laplace transforms. So step 1, write f of t in terms of uc of t. So here again, you start with 0. The value is 0. And then at t equals 5, you jump by how much? Well, it goes from 0 to 5. So we jump by 5. So that gives us a plus 5 u5 of t. And then at 20, you go down from 5 to 0. So you jump by minus 5. So at t equals 20, like here, you jump minus 5. So minus 5 u20 of t. Kind of like Super Mario. Whoop, you jump up, and then whoop, you jump down. And so here again, what we have, our function f of t then becomes 5 u5 of t minus 5 u20 of t. In particular, we can take the Laplace transform of f. So what this becomes is, let me make this box a bit bigger, perfect. We then get that Laplace of f looks different. So Laplace of f of t then becomes 5 Laplace of u5 of t, and then minus 5 Laplace of u20 of t. And here we just use the Laplace of the Heaviside function. So it just becomes 5 e of minus 5s over s over s, and then minus 5 e of minus 20s over s. And again, here we have a common factor just to simplify our work. Otherwise, you just do everything separately. So here what we get is 5 over s, and then e of minus 5s minus e of minus 20s. Very good. So now we Laplace the ODE. So once again, we take the L. Step 2. So take the L. So what was ODE? It was y double prime plus 4y prime plus 5y equals f of t. So now L of y double prime plus 4L of y prime plus 5 L of y equals L of f of t. And the good news is, so we have all the pieces that we need. So this becomes s squared, remember, L of y minus s y of 0 minus y prime of 0, and then plus 4 SL of y minus y of 0, and then plus 5 L of y. And again, L of f of t, we found that already. So 5 over s, I think e of minus 5s minus e of minus 20s. And once again, some terms simplify because y of 0 is 0, y prime of 0 is 0, and here also y of 0 is 0. So what this becomes is simply s squared plus 4s plus 5 L of y is this other Laplace transform. So 5 over s e of minus 5s minus e of minus 20s. And once again, sanity check. This becomes auxiliary equation. And so in the end, what we get, L of y becomes 5 over s times s squared plus 4s plus 5 times the exponential terms. E minus 5s minus e of minus 20s. And the rest is just this unveiling. So once again, we want to do partial fractions. So I think step 3. Partial fractions. So once again, just like before, we want to focus on the term without the exponentials, and then we'll introduce the exponentials. So focus on 5 over s times s squared plus 4s plus 5. Well, here again, you split it up. So it's just a over s plus bs plus c over s squared plus 4s plus 5, because you can't really factor out s squared plus 4s plus 5 more. And once again, you put it on a common denominator, compare all the terms, again, which you can see the details in the notes if you wish. And you eventually obtain that a equals 1, b is minus 1, and c is minus 4. So what that tells you is 5 over s times s squared plus 4s plus 5 is 1 over s plus minus s minus 4 over s squared plus 4s plus 5. Very good. And now let's see what to do with that. So step 4. So what do we have? So far, L of y was this fraction that we fractated times the exponential terms, but now the fractions part from the previous step becomes 1 over s, if 1 minus s plus 4 over s squared plus 4s plus 5, and then times the exponential terms. Minus 5s minus e of minus 10s. And again, we worry about the exponential terms later. First, let's focus on the stuff inside, which we want to write as a Laplace transform. So 1 over s, that's the Laplace transform of what? Well, that's just the Laplace transform of 1. One of the first examples I did about that. So the big question is, what about this other fraction? So s plus 4, s squared plus 4s plus 5, that's the Laplace transform of 1. So because we cannot really factor out the denominator more, the trick is to complete the square. So this was this completing the square trick. So this becomes s plus 4, s squared plus 4s plus 5. If you complete the square, down the square. Look how cute. It's literally a square. Okay. We get s plus 4. Again, s squared plus 4s plus 5. So it's s plus half of 4, which is 2 squared. And then minus 4 plus 1. And that is s plus 4 over s plus 2 squared plus 5. Sorry. So minus 4 plus 5, that's 1. Okay. Now, remember here the denominator is more important. So what do you want to do? You want to write this in terms of s plus 2. S plus 2. Now here it's not too bad because s plus 4 is s plus 2 plus 2. But in general, what you would use is s plus 2 minus 2. So it would be s plus 2 minus 2 plus 4. So indeed, s plus 2 plus 2 over s plus 2 squared plus 4. Plus 4. Which you will see soon. You can split up. So that becomes s plus 2 over s plus 2 squared plus 1 plus 2 over s plus 2 squared. I know it looks very complicated, but I promise we did an exercise like that before where we completed this square. So now, what is this? So you see a shift going on. So this is a shifted version. By how many units? So not 2, but minus 2 units. Because remember, s plus 2 is s minus minus 2. Of what? Of the unshifted version, which is s over s squared plus 1 plus 2 over s squared plus 1, which remember is the Laplace transform of cosine of t plus 2 sine of t. So what is the shifted version now? So this s plus 4 over s squared plus 4s plus 5, which again was this s plus 2, etc., now becomes the Laplace transform of, remember, extra exponential term. So e of minus 2s times cosine of t plus 2 sine of t. So that's the only ingredient we still needed. Now we can finally go back to the ODE. I know it's very long. I'm so sorry about that, but again, don't judge the messenger. Yeah. So back to the future. So what did we have so far? So far, L of y was 1 over s minus s plus 4 over s squared plus 4s plus 5 times the exponential terms. So e minus 5s minus e of minus 20s. All right, and remember what this becomes. So 1 over s was Laplace transform of 1. The other term is e of minus 2t cosine t if you want, and then minus 2e of minus 2t sine of t times e of minus 5s minus e of minus 20s. And remember, this becomes very long, so let's call all that h. So this is L of h of t times the exponential terms. So e of minus 5s minus e of minus 20s. Again, and please write down where h is, what h is. So where h of t is 1 minus e of minus 2t cosine t minus e of minus 2t sine of t. And then remember, what does the exponential term do? It shifts and jumps. So this is the same thing as L of h of t minus 5, u5 of t, and then minus h of t minus 20, u20 of t. And then u20 of t. And that is our solution. So what is our solution? It's just this in terms of h. So step 6, solution. So y of t is h of t minus 5, u5 of t minus h of t minus 20, u20 of t, and again, where h of t is 1 minus e of minus 2t cosine t minus e of minus 2t sine of t. So you see, h is usually the function we see in solutions of differential equations. And what this is saying is you just shift and jump this function h. Perfect. And once again, this has a very cool interpretation in terms of the picture. So what does our solution look like? So once again, before 5, so maybe this is 5, it's the solution y is 0. And then between 5 and 20, it has this transition regime. So maybe it goes up like that, then it goes down. And then after 20, it's just sinusoidal, like that. So this is our solution y of t. So once again, constant. So on this first thing, we have a constant regime. And here we have a transition regime. And then we have a sinusoidal regime. Technically, sinusoidal with damping because of the exponential term. Just like you would expect with oscillators with damping. I know it sounds like an empire, but no, it's really not. It's just fun with differential equations.